So, good morning, everyone. Very a warm welcome to the Learning from the Extremes webinar. Today, we are going to have a passionate one about observing with robotic telescopes, and we hope that you enjoy us. Please use the chat to communicate with us and with the presenter if you have any question. You also see a form where we are asking you to please register and manifest your interest to participate in future webinars. We have a very nice series of webinars for you to follow. These webinars are going to take place every 2 weeks, but this one is an exception. It's taking place in the morning because we have time on the telescope that is in Australia, and that requires us to be here in the morning. The next webinars are going to take place at 4 CET to suit most of you here in Europe, and they are going to occur every 2 weeks. Another exception is the next one that is going to take place next week, and in that one, we are going to teach you how to handle the images that we are going to acquire today. So today, you're going to hear about robotic telescopes, how you can bring this super Rolls Royce to your classroom, to your students. And next week, we are going to tell you how you can process the images that we are going to acquire today. And if you are one of the Learning from the Extreme schools, ask us to join you in your school, somehow online or face-to-face, and we will be very glad to welcome your students to join us. Actually, this is open to any school. If you would like a session, a live session with your students, let us know, and we will be thrilled to be there for you. So today we have here with us Fraser Rules. He's one of these crazy people who love studying black holes. He's been observing black hole candidates for quite some time, but he's also an expert in working in the educational program of the Faulkes Telescope. And I'm not going to give any spoilers because Fraser is going to be the one presenting me to you. Fraser, thank you very much for agreeing to be with us this morning, and the floor is yours.
Rosa, how how can I lose after an introduction like that? Brilliant, thank you. Yeah, absolute pleasure to be here as always, working with you all. I'm going to share some slides with you. I know you probably don't want to hear slides and see slides, but I'm going to do that. So hopefully they will come up on your screen around about now. And what I will say as well.
Not in presenter mode yet.
No, I know. There we go. Okay, that's good, right. If you have questions, Rose, actually, you know the mechanism, but they can anyone who has questions can ask the questions as we go along, and you can forward them on to me.
They have the chat on YouTube. Yeah. Just post there, and we'll be following and accompanying any emergency question. I will let you know. An
emergency question. Okay, I'll look out for an emergency question. That's the kind of question I worry about. But yeah, if you have questions, and Rosa will tell me because I speak too fast because I get excited. So I will try and talk reasonably slowly, sensibly. I will answer questions as we go along. I may not see the questions. I generally, when I have the screen in PowerPoint mode, I don't see the questions, but I know Rosa and Gustavo will jump in and ask those questions. So yeah, the plan today, and it's kind of, I guess, so far so good, but the plan today is to go over to Australia, virtually at least, in about 40 minutes time, about 9:45 in Portugal, the UK, 10:45 CET. And at that point, I will then show you how one of our telescopes works in what's called real-time mode. So I'll be driving the telescope. But the reason for doing this isn't really to show you how clever I am or how clever the telescope is. The reason is to show you how easy it is and how straightforward it is, and that you as teachers, wherever you are in, I was going to say in Europe, but I mean, let's take it even further. If there are people watching from further afield than that, you can work with us. You can have time on the telescopes yourselves as educators. Everything that we'll talk about today is free of charge. I think that's the case with the image processing that Rosa was mentioning that we'll be discussing next week. The only slight difference to that is sometimes we talk about Photoshop, but again, Photoshop is not the only image processing software out there. So I think Rosa will be showing you free versions of software, but obviously Photoshop is kind of the top of that level. That is the one that costs money, but there are free alternatives. I think all the software that we'll talk about, we won't talk about software much today, but maybe more next week, is designed to work on, let's see, Windows, Linux, Mac, tablet, and probably mobile phone. Some of this stuff works on mobile phones, some of it becomes a little bit tricky to do on mobile phone, but there are lots of options there for you. And again, depending on your circumstances, where you live in Portugal or further afield, you may have very good Wi-Fi, you may have not so good Wi-Fi. So that hopefully helps you in terms of access. So I'm Fraser Lewis. As Rosa mentioned, I've been working with Rosa and Gustavo, certainly Rosa for probably about 10 years or so, Gustavo maybe 8 years or so. I'm based in a city called Cardiff in South Wales, and our telescopes are all around the world. I'll tell you a little bit more about the telescopes as we go along. The group I work for mostly is the Faulkes Telescope project. You see the logo top left, and I will try and provide you with some links for this as we go along, or again, Gustavo, Rosa, by all means, put links into the chat if you want to do it that way. And there was something else I was going to say about that. Yes, I will make sure that, as well as the recording, that you can get copies of the slides afterwards as well. Sometimes people like those to be able to access those. So this is a little bit about our project. We could probably do an hour on the project and its reach and its history and what we do and what we want to do. We'll keep it a little bit shorter today. It's effectively what I say on the right-hand side there on this screen. We provide telescope time for free. We provide it to teachers. I say other educators. So if you're working with schools, if you're working with community groups, youth groups, if you are sort of a private or a freelance educator, we will work with you in any way that we can. When we started up, it was UK and Ireland. We then kind of moved into working with schools in the European Union, particularly with Rosa's groups in Portugal, and with our colleagues in EA in Greece as well, and then with various other countries. We've gone a little bit more global. We will work pretty much with anyone who wants to work with us. So don't think that there's an issue in terms of where you are based in the world. As well as providing the telescope time, as well as allowing you access to the telescope, we try to give you instructions. It's probably a little bit more fair than to just give you a telescope and say, go, enjoy. So we've given you some resources. Many of them are on the web link at the bottom of the page there. There's a program that we're running at the moment called Last Skill. I can't quite remember the name of what way we came up with Last Skill. I can't remember the wording, but it's basically from a couple of years ago. It's an Erasmus Plus program where the UK, us in Cardiff, are the lead, and we are developing resources to use online in areas such as data processing, with the idea of big data. When we had the pandemic and we all had to stay at home and do things online, a lot of people started changing the way they work and the way they think. So we provide you with lots of access to information. If you're interested, or even if you're not interested, please have a look and become interested in Last Skill. There is a web link at the bottom there that links to a page called Tools, where we list about, I think about 20 or 25 different tools, online apps, pieces of software, programs, websites, and so on, all to do with astronomy, all to do with astronomy and observing and think, and the process of how you think in astronomy and STEM, and then some background ones in sort of some clever ways of teaching, innovative new ways of teaching and working with your students. Let me move on to sort of my specialist area, if you like. We work with things called robotic telescopes. So robotic telescopes are telescopes that don't really have somebody sitting in the way that I'm sitting in front of a laptop. They don't really have somebody sitting in a building next door or in the observatory dome itself. What we have with these robotic telescopes, they have a degree of independence. They work what we call remotely or robotically. If you think about this, it's a bit of a strange concept. If you think about it, I guess every space-based telescope, so things like Hubble, things like James Webb Space Telescope, they are all robotic telescopes. We are not going up there and driving these telescopes. In the case of Hubble, of course, we did send some missions to fix it, but in the case of James Webb, we can't do that. So robotic telescopes are on the ground or in space. So we have a set of these objects on the ground. There are 3 dots on the map. You may see them, hopefully they're little red dots. The 2 red ones represent the 2 2-meter telescopes within our network, called the Faulkes telescopes. One is on an island in Hawaii. It's on the island of Maui, and on a volcano called Haleakala. And the other one is the little red dot in Australia, is in New South Wales. So about 2 hours or so drive up from Sydney into the hills, and that is a 2-meter telescope in Australia. So we have the northern and southern hemispheres covered. That's kind of useful, because if you've ever been to the southern hemisphere, or if you worked with people that have been there, or you speak to people that are there, or even if you're from there yourself, you'll know that the sky is different. We see different objects in the night sky in the south than the north. There are different objects, and there are kind of some quite interesting objects in the southern hemisphere that we wouldn't be able to access from, let's say, Europe and North America alone. There is a 3rd dot on the map. It's a yellow telescope, or yellow dot there. That is known as the Liverpool telescope. That's on the island of La Palma in the Canary Islands. That's run by a different group. It's some colleagues of ours. We work quite closely with them, but they are based up in Liverpool. They run a program called the National Schools Observatory. I think I might mention it in one of the slides later as well. But just to give you a feel for sort of the range of where these telescopes are, what you may already be thinking is, well, actually, these are really nice places to visit. Quite like to go to Hawaii. I'd quite enjoy a trip to the Canary Islands. I'd quite enjoy a trip to Australia. And one of the reasons for that, maybe you're thinking, is, well, the weather's really nice there. It's always blue sky, always, but mostly always blue sky. It doesn't rain much. It's not cloudy. It's probably somewhere that there aren't lots and lots of flashing lights and city lights and chemical pollution. And that's kind of why we put the telescopes there. We put the telescopes in places on the Earth's surface where the weather is better, where there is no pollution, whether it be light pollution or chemical pollution and so on. So that's why you start to see telescopes clustering. We wouldn't put telescopes in the UK, not in the optical waveband. As I look out of my window today, it's kind of grey. It was blue yesterday. It was grey on Sunday. So, we don't have the weather for that. Where the UK has led in astronomy in the past, aside from actually developing instrumentation, is in the radio, because in the radio, it doesn't actually matter whether there's cloud. You can actually peer through the cloud in the radio. So UK has some very big and very good radio telescopes, but in the optical, there aren't too many here at all. One more thing I'll mention, I'll just remind you, and maybe you're familiar with this, maybe not. I'm talking about 2-meter telescopes. 2 meter is the diameter of the mirror. So the telescope is made up of a mirror and some lenses and a camera and some metal that kind of supports it, keeps it all held together. I'll show you some images in a second of that. But this mirror, this 2-meter mirror, is the collecting area. So the bigger your collecting area, the bigger your mirror, if you like, the more photons you can collect, or the more efficiently you can collect photons, or if you want to think of it another way, the more quickly you can collect photons. So very broadly, and there are people here who will shout and scream that I'm wrong, but very, very broadly, the bigger your telescope, the bigger your mirror is, kind of the better the science you can do, or the better the images you can take. Now, that's not entirely fair, because you still need a good camera, and you still need to put your telescope in what we call a good site, somewhere that has this good weather. But broadly speaking, a 2-meter telescope will collect light more rapidly, more efficiently than a smaller telescope. I'm going to try and prove that that's not entirely the case later, because we'll actually be observing on a smaller telescope today, a 40-centimeter telescope. But these 2-meter telescopes I was going to say unique. I guess there's 3 of them, so maybe they're not unique, but they are reasonably rare. The size of telescope that is available for you to do education, 2-meter telescope is about as high as you can go, unless you have, a cousin who works in NASA, let's say. Here's an image of our site in the USA, in Hawaii. Our telescopes are the two small white buildings towards the bottom of the image. You see them written there as the Faulkes Telescope. That is what you get, or what we got, let's say 20 years, just over 20 years or so ago. That cost about £5 million. So let's say 6 million euros, 5.5 million euros, something like that. So again, that was an expensive piece of equipment. The money initially came from science funding within the UK, but also, in fact, mostly from our benefactor, who is a guy called Dill Faulkes. And that's why the telescopes are named after him, because obviously he put the money in. So this is our site in the Northern Hemisphere. You can kind of see that it's a volcano. You can kind of see it's sort of rugged and very brown and very sort of dusty, well, not dusty site, but a very brown site. All the rest of this facility, all the rest of the buildings you see in this image, most of them look like telescopes, if you like telescope domes. They are US military. So I think we're the only kind of civilian, or the biggest civilian piece of equipment that's on this mountainside. This site is at about 3,000 meters above sea level, 10,000 feet or so above sea level. And you can probably make out in the background, if you see the blue sky in the background, there's a lot of white cloud. So in some parts of Hawaii, down at sea level, they would be sitting under cloud. And yet here we are at 10,000 feet, and we're actually getting above some of that low level weather. And we're getting above some of the atmosphere. The atmosphere of Earth is very good for us for lots of reasons, such as it provides us with oxygen and it protects us from UV and X-ray radiation and so on, and cosmic rays. But the one thing the atmosphere does that isn't great for astronomers is it stops that light, or it slows down, it blocks some of that light out. So if you can get above some of that atmosphere, that's actually a good thing. I'm just going to grab a mouthful of coffee. Are there any questions at all so far, Rosa or Gustavo, or is it all quiet so far?
No questions yet. We have several people in the audience, but no questions. Just a good morning from everyone.
Okay, good morning. Well, yeah, good morning. Bom dia. Buenos dias.
Now you have to do it in Greek.
Kalimera.
Well.
Kalimera, guten Morgen. Do you know, I should say Bore da, which is the Welsh. It's our national day today. So you're very lucky to have me, because yeah, it's our national day. So it's not a lot changes here, but hey, yeah, so it's our national day. So yeah, Bore da, which is the Welsh for good morning. And my colleague Sarah, if she's watching, will be delighted to know that I've at least tried that bit in Welsh. I can't go much further. Here's an image of one of our telescopes. This is one of our 2-meter telescopes sitting in a factory near Liverpool when it was being built. So they built it completely in Liverpool. You can probably see that there's some of this roof actually opens as a telescope would. They controlled it, they made sure everything worked, and then they kind of broke it all down, put it in boxes and shipped it across to Hawaii, and then the other one to Australia. Like I say, it cost about 6 million euros or so. There's some technical information on the slide. Now, again, if you come from an astronomy background, some of those words mean something to you. If you don't, they don't. And I'm not going to go crazy and try and explain too much about what's going on here, but there is lots of information on the web link at the bottom if you do want to know more. But the idea is here just kind of the filter system and the cameras that we use. So you can see the guys stood next to it there, so you can see something of the scale of this object as well. Let's try and break this up. Let's try and make this a little bit more interesting and a little bit more lively. I know we have teachers today. I don't know if we have students and pupils as well. If you do, then they're probably bored thoroughly by now. So let's show you some images and talk you through a few of these images and what they are and what sort of things we can take, what sort of pictures we can take, if you like. So this may be one you recognize. This may be an object that you recognize, particularly if you grew up during Hubble, during the main first few years of Hubble. Hubble produced lots of beautiful, amazing images of objects in the night sky. This is one of them. It's a black and white image. We'll talk a little bit more about what that means and why that is, and how Rosa and I can turn black and white into color. because we're mad, because we're magicians. We'll tell you a little bit about that next week as well. This is an object called the Eagle Nebula, also known as Messier 16. So there's a catalog of objects called the Messier catalog, and M16 is one of them. It's known as the Eagle Nebula, or the Pillars of Creation. And you can see these kind of three structures, pillars, if you like. I should have done more my homework and have numbers for you about how big this is and how far away it is. I apologize, I don't remember those numbers off the top of my head, and I'm not going to try and do it for you in real time. If you look on, let's say, Wikipedia, but lots of other websites out there as well, of course, you will find lots of information on objects such as Messier 16. It's a star forming region. This is an area where stars are actually still switching on. You'll see it. I've got another image in a minute. You'll see it a bit more clearly. But this is an area where we look at, we see these clouds of gas and dust, which is primarily hydrogen. And we know that stars are made, again, primarily of hydrogen. So when we see these columns of gas and dust, they are ideal factories, laboratories, birthplaces of stars. So that's where we see here this kind of idea seems to go across most curriculum. If you're in Greece, Portugal, Spain, wherever you are, we always seem to find that teachers are able to talk about the life cycle of stars, how they are born, where they are born, how long they live for, and kind of how they die, and what they leave behind, if you like. And what they leave behind is the bit where I start to switch on, because that's the kind of the black holes and the neutron stars and all the exciting stuff. But everything that comes before that is kind of fun and interesting as well, of course. So this is M16. It's a black and white image taken from our telescope a few years ago. That's the color version. So again, you can kind of see some color in that. You can see different colors of in the object. They start to correspond to some of the elements. It's not a perfect scenario, it's not a perfect solution, but when we see red, when we see lots of red, especially around star forming regions, that starts to tell us about hydrogen. That starts to suggest there's hydrogen. There's not so much in this image, and again, some of this is down to the way it's been processed, but sometimes you see this as a very green image, and that starts to suggest oxygen. There's a particular electronic transition of oxygen, O3, that sits right in the middle of the green part of the visible spectrum. So green starts to suggest oxygen, red starts to suggest hydrogen. Now, there's a little bit more to it than that, but we're sort of going down the route of chemistry, astrochemistry, which won't be very successful for me if I try to go too much further. This is a color image. This is taken from our telescope and sort of processed, and some of the processing is more artistic. Some of it is scientific, so we're doing real science. Some of it, when you start to sort of combine colors and play around, like I say, Photoshop or Salsa J, which is another program that we use that does this for free. There's an element of artistry in there. There's something I really struggle with, but you can become quite good, and you will have students who maybe don't really buy into astronomy, but really, really want to play around with the images and make artistic and beautiful pictures. And that's obviously a very good thing to do as well. That's the Hubble image. So that's what you get for, let's say, £5 million. That's what you get from Hubble. It's the same object. Hubble, again, I can't remember the numbers off the top of my head, and they are so out of date, it probably doesn't matter. But Hubble cost, I think, in the region of billions of dollars. So not millions, but billions of dollars. And I know we went back to Hubble, I think, on 4 occasions to do some extra work and to change the lenses and the cameras. And I think each one of those was maybe of the order of 500 or so million dollars. Okay, I know dollars and euros are not the same, but they're pretty close. So that's the kind of cost you have for Hubble. Now, I'm not saying our telescopes are as good as Hubble. I wouldn't say that. And if I did, my phone would be ringing with somebody from NASA in the next 10 minutes saying, please don't say that, it's not true. But as teachers, as educators, we don't really have access to Hubble, not to actually control it, to drive it, to get it to go where we want to go. We can get at the archive, we can look at the data, but we can't control it. But we can control the Faulkes telescopes, and we can drive those. And that's the key here, is that maybe our images are not absolutely as perfect as Hubble, but they are pretty good. They are pretty close. So let me talk a little bit more. So
Fraser, there is a question
yes,
here.
go for it. Yeah, by all means, go for it.
Asking if you can operate work with both with telescopes simultaneously. So
Oh,
if the telescopes work simultaneously.
I can't multitask that much to do it. But if somebody was sat next to me, yes, in theory you can. But because of the times of day that they operate, we don't tend to do that. I'll maybe try and answer the question a little bit more as we go along, but yeah, that's a really, really good question. Yes, each of the telescopes works independently. Each of the telescopes actually has kind of what we call a queue. It has a series of requests, observations. They come in from teachers, from educators. But in the case of most of the telescopes, about 80–90% of the work they do is science. And those objects are programmed in, are requested by scientific groups all over the world. I was going to say all the big universities. That's probably not far off the truth. Most of the big research groups are working on, if not our telescopes, at least telescopes that work in a very similar way. So yes, in theory, you could drive two telescopes at the same time. You're limited to where the telescopes are located because, of course, do a little bit of geography here. The reason that we're talking about using an Australian telescope is that right now it is, I think, 10 hours ahead of us, which makes it 7:28 p.m. So 7:30 in the evening in Australia. It's also just coming out of, no, it's just coming out of summer, isn't it? It's just heading into their autumn. So 7:28 in the evening, the telescope has just opened. So we're able to control that telescope. We do generally run these slots at around about 9:30 or so in the morning, UT, 10:30 or so CET. And another set of telescope time that we use is around about 3 p.m. So at the end of your school day. So 3 p.m. UK, Portugal, again, maybe 4 p.m. CET. At 4 p.m., yeah, I guess Australia is still open because it's just after midnight. But also at 4 p.m., our Hawaiian telescope, now Hawaii is 10 hours behind us, which makes it about 6 a.m. I'm almost having to do this on pen and paper. It makes it about 6 a.m. in Hawaii. So again, it's just about dark. It's just that edge. It's this sort of what we call, dawn is almost coming at that point. So it's just that sort of twilight edge there. So yeah, there are probably times of the day where you could drive both telescopes. I don't know what the question is directly asking. I wonder if maybe it's to do with asteroids. And we have kind of played around with this in the past a little bit, that you can take images of the same object from different parts of the Earth's surface. And because asteroids are quite close to us and moving quite rapidly, you can do a thing called parallax, where you can kind of start to understand something about the motion and the distance of this object by drawing a triangle. So maybe it's that. I wouldn't advise for beginners driving two telescopes at the same time. I think that might be quite a tricky thing to do. But yes, in theory, it can be done. There are lots of telescopes in the network, but only a handful that are used in this real-time mode that I'm describing today. I'll try and talk a little bit more about the other way we drive the telescope as we go along as well. So yeah, I'll maybe sort of revisit little bits of that question as we go along, but hopefully that gives you a little bit of an answer straight away. I mentioned before about life cycle of stars. And I talked about star birth, if you like. I've gone right to the other extreme now. I've gone to star death. When stars die, there are two ways they die. Our sun is a low mass star, if you like. There's a line at around about 8 solar masses. So objects that are stars that are less than 8 times the mass of our sun are going to die in a fairly gentle way. Might not be that gentle if we're nearby, but in astronomical terms, a relatively gentle way. They're going to leave behind an object called a white dwarf and potentially a planetary nebula. Objects that are more than 8 times the mass of our sun, stars that are more than 8 times the mass of our sun, when they die, when they finish their lifetime, they explode. That's what's called a supernova. You may have heard the term supernova. That's what it means. It's an object that was a star, a very massive star that simply is unable to support its own itself, because of conflicting forces within it with gravity and the way it's producing energy, liberating energy, they die in this form called a supernova. And this is what's called a supernova remnant, what you see on the screen right now. This is an object called M1, Messier 1, or the Crab Nebula. It's in the constellation of Taurus. It's not visible to the naked eye. This is what you get by taking an image. There are bits of red and green in there, which again maybe says hydrogen and oxygen. There are a few other colors in there, and we can start to do some good science based on the chemistry of this object. The other beauty of this object, this was discovered, this was seen in the night sky by astronomers in China in the year 1054. And again, probably asking a lot to do the maths in real time, but that's nearly 1,000 years ago. 1054, yes, it's about 970 years ago. That's really good for astronomers. We actually know almost to the day when this object was first observed. That gives us a really, really good data point, because we know how old this object is. We can start to do some clever things about its size and its distance and so on, based on the fact that we know it was around then. So this is an exploding star, like I say, a supernova remnant. We'll talk a little bit maybe more about those as we go along. I'm sort of jumping through a couple of slides. I'm kind of keeping an eye on the time as well, because I've got 12 minutes or so before we jump over to the telescope. This is a galaxy. It's known as a spiral galaxy. It's not our Milky Way. A lot of people, when you ask them the question, they say, oh, it's the Milky Way. Well, it's not. It looks quite a lot like how we think our Milky Way looks. But it's very hard for us to take an image of our galaxy. To take an image of our galaxy, we'd have to fly a spacecraft out of our galaxy and turn around and look back. And we don't really have the technology to do that yet. But we think our galaxy looks a little bit like this. It has this very bright central region, and we have a feeling with most of these galaxies that there is a rather large black hole of the order maybe of, let's say, 1 million solar masses, but that number can change in either direction. And then it has these spiral arms, and the spiral arms are where we start to see this idea of star formation. So if I remember rightly, I think this is M51, the Whirlpool galaxy, and it looks a little bit like how we think our galaxy is, with a few little changes here and there. So we've sort of looked at star birth, we've looked at star death, we've looked at places where there are, let's say, billions of stars. With some of these galaxies, I think you can say trillions, but my head starts to hurt. It's way too early in the morning to be thinking of trillions. So let's say million is a 1 with 6 zeros, a billion is a 1 with 9 zeros, and then a trillion is a 1 with 12 zeros. So a trillion is a million million. Okay. That's probably enough maths for this morning. Sort of going back to the question about telescopes and sizes and where they are and how you control them. In late 2000s, so around about maybe 2008, we sort of moved our telescopes over to a network. We started working with these guys, or they kind of effectively came in and bought us out, I guess. They're called Las Cumbres Observatory. They are based in Northern California, and they are developing, or have developed, I guess, a network of telescopes all around the world. A group of 2-meter telescopes. There are 2 of them. There are, I think, 10 1-meter telescopes and maybe about 12 or 14 40-centimeter telescopes. They are dotted around the world. Again, they're dotted in all the places where there is nice weather: Texas, Hawaii, Chile, South Africa. They've done this for a couple of reasons. One is, if you, the English saying, the British saying, I guess, is putting all your eggs in one basket. If you built 20 telescopes on one site, doesn't matter how good that site is, if there is cloud, if there is a failure of electricity, if there is a failure of internet, you lose all 20 telescopes for the duration of that. If you put those 20 telescopes in 6 or 8 different places around the world, you get around the fact that maybe one place just has really rubbish weather for 2 weeks, 3 weeks. We've seen this recently, and we see it even now with Mallorca, and I think the Canary Islands experiencing snow and cloud and so on. So that's one reason you do it. Another reason is we're interested in the northern and southern skies. There are different objects to see in terms of the beauty of them and in terms of the science. The other aspect of this, myself, Rosa, maybe not so much Gustavo, but certainly myself and Rosa, and a lot of the people at LCO are interested in what's called transient astronomy, objects that change in brightness very rapidly and often without any prediction, without any foresight that that was going to happen. So that galaxy I showed you before, if we go back and take an image of that galaxy in 1,000 years, 10,000 years time, it will look almost the same. Okay, maybe the technology is not there for us to do that just yet, but it will look pretty much the same. But there are objects that change in brightness overnight, or between now and 10 o'clock UT, or between now and 9:38 UT. There are things like asteroids, there are things like supernovae, there are things like gamma ray bursts. I'm missing a few, I'm sure. There are objects such as exoplanets. There are these things that Rosa and I study, which are binary systems where one of the components is something a bit exotic, like a black hole. These objects change in brightness from one day to the next, from 1 week to the next. So if you put your telescopes in different places around the world, you will always have telescopes that are sitting in darkness. Okay, so right now, if we look at the map, Tenerife is in daylight, South Africa is in daylight, Israel is in daylight. We don't have any telescopes in Asia just yet. Australia is Wednesday night. Chile is 4 or 5 hours behind us, so that is Wednesday morning. Hawaii, it's around about midnight. And you can see as the day goes on, so different telescopes go into darkness and come out of darkness and so on. So that's the idea is that here. They've built this network of multiple telescopes, 1 meter aperture, 40 centimeter telescope, which is a little bit more for the educators amongst us. And then the 2 meter telescopes, which are the really big toys as well. So that's the idea of their network. As the way we kind of moved our telescopes over to their network, we retained a set of time, an amount of time on those telescopes. And it's that time that we use with educators. And again, I've said it before, let's say it one more time. That time is not charged. There is no point at which you use telescope time and then we send you an email and say, please send us 600 euros. So if you have an email like that from us, it's not real, I promise you. What we do ask sometimes is if we give you an allocation of time, which may be a couple of hours per 6-month block, which is quite a decent amount of time. If you get through that time quite quickly and you ask us for more time, we can often say yes. What we say is, yes, you can have more time, but what we would like from you is an image of you working with your classroom, or some interaction in an activity we're doing, or something that we can put on social media, something we can share with our fellow users. So there's sometimes, it's not a price as such, but there's sometimes this opportunity to just say, okay, we will give you more time, but let's just get something, let's see what you're doing and help and see if we can interact and get you working with us, other schools as well. So we're at 9:40, which means we're 5 minutes away. I feel like I'm building this up and then it's going to fall. I'm going to drop. I'm not going to go into that slide just yet. I think now is a really good time to jump over. I'm also concerned I've been speaking for a while. So if there are any other questions at this point, Rosa, now would be a really good time to jump in. I'm just going to stop sharing this screen and I'll start sharing my internet browser. Is there anything at all that
No questions?
No, they're a quiet group.
Yeah, so maybe you can then continue at this point, although there is a delay between what you're presenting and here on YouTube, but it's not so big. So no, there is no questions at this moment.
Wow, okay. That's rare. Normally by now I have 20 or 30 questions.
Well, they are all waiting, expecting for the moment.
So let's go with that they are captivated. They are hanging, what we would say is hanging on every word, right? But yeah, please do ask questions. And again, I know Rose has mentioned before, some of the teachers here are not from places where you've come across astronomy before or done much astronomy. So your question that you might want to ask feels a little bit basic or a little bit simplistic. Don't worry about that. Rosa is not telling people or not shouting out the names of people that are asking questions. So if you do have a question, I'm more than happy to try and answer it. I'm share, hopefully you see another screen right now, which sort of says siding spring at the top and
Yes.
then some numbers.
Yes, we do.
Okay, so this is the weather monitor. This is all the different, this is where robotic telescopes come into their own. We don't need to have somebody sitting in Australia at, I guess, 8 or 9 in the evening. All the weather monitoring, all the weather information we need is done from sensors, electronic sensors. We are measuring the air temperature, the wind speed, the wind direction. We are measuring humidity. Humidity sort of relates to how much water there is in the air, but it also gives us a feel for cloud and for rain, which obviously are reasonably bad things to have when you have a £5 million telescope. All these numbers being, if you like, good, all these numbers being in the right sets of values mean that right now the telescope is open. I can see that because there is a blue and a gray line. The blue line on that top graph, if you can see it, is when the telescope is open. The gray line is when it's closed. The gray line here for siding spring for Australia corresponds with the time at which it was daylight. Optical telescopes don't work in the daytime, not at least not the ones that we have, because there's nothing to see. The only object to see is the sun, and that's sort of a sort of a separate field of astronomy, if you like. So our telescope is open. I will go over to another screen here within the screens I'm doing. Within 5 minutes of the session starting, I can click on begin session, and we come up with an image or a set of objects that look like this. So in astronomy, as with traffic lights, as with driving along the road, green is good and red is bad. Green for go, red for stop. So right now our observatory is green, it's available. The other ones that say status unavailable, I'm not sure. They will probably, hopefully, come good in the next few minutes or so. Our session is due to start at 45, which is in about a minute's time. On the left-hand side of the image, you can probably see a circle. It's an all-sky view. It's a camera that is on the ground that is looking up, but is so wide a field of view that it actually takes in some of the buildings around it. So that shows something about the way the night sky is in Australia. There's a very bright white blob on the left of the image. You may guess what that is. It's an object that prevents us doing astronomy very well or very easily for a few days every month, and then it sort of goes away. It's called the moon. You may have heard of it. It's quite a useful object for some areas of astronomy, but for others, such as having a really dark sky, it's not so good. So this is my slide, or sorry, this is the screen that I have. These are the bits of information I'm going to need to type in. I'm just waiting to see the countdown. This is this sort of 10, 9, 8 business that we do as astronomers to get people excited. When this clicks over to 9:45, I'm hoping that we start to see more green. Good. Okay, we see more green. Again, green is good, yellow is okay, red is bad. There's no red. Okay. So I'm going to pick an object. Now I've done this in advance, and this is where it gets tricky because I cannot type and talk at the same time. Some people would suggest I can't do either of those very well individually, but at the same time, no, not a hope. So I'm just typing in some numbers. You'll probably see them going in there. I'll tell you a little bit about those numbers as we go along, just to give you a fighting chance of understanding what's going on. I'm clicking on filters. Now, again, when we talk about color imaging next, maybe a little bit more next week, we'll explain a little bit more about what filters do. And again, I've got some slides we can talk about at the end of this session as well. I had them in reserve. The reason being that I had them in reserve is that at this particular point, 30 or 40% of the time, the telescope is not open because of bad weather. Let's say 30%. As a teacher, of course, you prepare for any eventuality, any problem. So you can go straight to your backup activity, your plan B or your plan C. So I have a plan B and a plan C because I've done this enough times to know that it doesn't always work. I've put in some numbers. So I've put in the name of an object there. It's called NGC 1385. If you Google that or look on Wikipedia, you'll find out a little bit about it. It's just a catalog number of a particular object. I've then put in some numbers, 2 sets of numbers called right ascension and declination. They are the astronomical equivalent of latitude and longitude. So we can pinpoint any object on Earth. I know you have, what, 3 words these days, but you can pinpoint any object on Earth by the number of degrees it is around the globe and the number of degrees it is away from the equator. RA and DEC, right ascension and declination, is effectively the same system, but for the sky. And those numbers are available. And again, there are lots of resources out there we can point you at that start to explain something about this. And there are some really nice programs out there you can play around with as well. I've done my homework. Doesn't always happen. My teachers from school will tell you that never used to happen very often. But because there are lots of people in the room today, I thought I'd better do a little bit of preparation, try to look a little bit professional. Doesn't always work. If by doing that, I've pulled out some objects that I think will work. So I think this is an object that will work. Again, there always comes back the question, well, how did you know that NGC 1385 was a good object? How did you know to pick a particular exposure time? That takes a little bit more of an answering than we can maybe go into today, but I'm more than happy to try and give you some answers on that as we go along. Basically, what I've done so far is I've given the telescope some numbers. I've given the telescope a particular point in the sky to look at, and I've told it how long to look for. As I can see there, camera exposing 9 seconds left. So the camera is taking a 120-second image, a 2-minute image. Now, again, if you've ever played around doing this from a motorway bridge, you see that sort of thing where you do a really long exposure and you get all the car tail lights sort of going into the distance, a really cool effect. We're not collecting many photons, or we're trying to collect a decent amount of photons from an object that is 68 million light years away. So we need a 2-minute image to collect enough photons. And I've kind of guessed at 120 seconds. I don't know for sure it'll work, but in my head, it feels like a decent guess. So we've taken an image. It will hopefully be there. Yeah. So what do you think, Rosa? Is that okay? It's not awful, is it? It's not.
It's indeed very nice.
It is nice. See, the thing is, I'm really used to the 2-meter network, and the 2-meter telescope would collect those photons more efficiently, and the image would look a little bit more obvious.
You're spoiled.
I'm spoiled, but what I do get with the 2-meter image is what we call a very narrow field of view, a very small area of the sky. When I image with the 0.4 meter telescope, I get a field of view that is about, trying to do the maths, about 6 times larger. So I'm looking at a 6 times larger area of sky. So for some objects, the 40-centimeter telescopes are much, much better because the 2-meter telescope is too narrow. We can play around. What Rose and I maybe will do, we'll have a chat during the week, and we maybe start to play around with this particular set of images as part of how we explain how we do the image processing next week. I'm taking 3 images here. I'm taking an image in red, in green, in blue. I'm just checking to see what's going on. Let me try and explain a little bit about what I mean there. When you go out at night and you look up in the night sky, or you use a small telescope or binoculars, all your color receptors in your eye have switched off. All of those receptors don't work in low light conditions. Most of objects that we look at in the night sky are white blobs against a gray or a black background. But there is color there. We saw this with the images of M16, of M1. There is some color there, but it's subtle. It's quite a hard effect to pull out. I'm taking 3 separate images. Our camera is a black and white camera. It's not a color camera. Color camera would require much, much more money, I suppose, and much more technology to be able to do well. So the way we do color in astronomy is we use pieces of glass. We call them filters. We have a red filter, a green filter, and a blue filter, and we take 3 separate images of the same object. So what I'm going to end up with is 3 black and white pictures that all look a bit like this, but one of them will be in red, one of them will be in green light, and one of them will be in blue light. This is where Rosa's magical transformations start to happen. This is where she can combine those 3 images. I don't want to put pressure on her, but let's say she can do it in 30 seconds or so. She'll show us next week how quickly she can do it. She'll kill me for this, but she can add those images together and kind of recreate the color image. So that's what we do here. We can take an image in black and white, and funnily enough, for most science, black and white is fine. Black and white is okay. There are some bits of science that we want to do where we need multiple images, multiple filters and so on. But for most of our images, black and white is absolutely fine. We are measuring dots of light. We're measuring where they are. We're measuring how bright they are. We're measuring how much they change. Those things work quite well with just single images. Let's scroll back up. I think we had the second image. I think the second image came through. I didn't really spot the join, but we're on the third image. And there's 52 seconds to go. That bit there with that really odd looking kind of robot that says loading, there is normally a webcam. There is normally a webcam that sits in the telescope. Maybe it doesn't work on the 40 centimeters, only on the 2 meters perhaps. And that shows the telescope moving in real time. So something that the kids really seem to enjoy more than the images coming down is pressing buttons, sending some numbers to Australia and seeing this 5 meter, 25-ton piece of equipment moving in the night sky. And you can kind of put music in your own head to it as well, if you like, and just see how it goes. So yeah, we're missing that today. That's a shame. That normally works certainly on the 2 meters. So maybe that's the jump to the 40 centimeters doesn't allow us to see that. With 7 seconds to go, we should see the third image come in. So if you look at that image on the right-hand side, you might see it just jump a little bit. I'm waiting to see it. If anyone sees it, tell me, because I didn't see it. Okay. It's reading out. Okay. Maybe I missed it. Yeah, maybe that's a little bit different. We can explore these. What we can do, these images are really, really big. When I started in astronomy in 2004, these images came back from the telescope and they were 2 megabyte. And that was quite a large file, and it took a few seconds to download. And I think we went quite quickly to 8 megabyte, and they took forever to download. And I never did it at home. And even if I did, my girlfriend would shout at me about blocking up all the bandwidth. 8 megabytes is nothing these days, right? 8 megabytes, you know, your phone carries however many gigabytes of data these days. So these files have become bigger, and what we thought might have been a problem didn't actually turn out to be one. But we've ended up with images that are 100 megabytes or so. I'll come back to that. What I'm going to do, rather than keep on talking, I'm going to find another object. So again, this is from Fraser's magical list of objects that are going to work, and this changes every month, as you probably know from looking at the night sky. What's visible in March is not visible necessarily in August. So if I do this again with you in August, I'll probably give you almost exactly the same slides, but these will be very different objects. So I've put in some other numbers. I'm just checking they're right, because there's nothing that the telescope is going to tell me to say it's wrong. It will go where I tell it to go. I've put in some exposure times. I've pressed go. This is going to take 599 seconds to complete. 600 seconds, 10 minutes. Okay, that's fine. So that gives me 10 minutes more to talk to you. Again, we're all green here. The telescope is moving to target. Okay, so the telescope's got there. It's got to the new object and the camera has opened. So I want a 3-minute exposure in each of red, green, and blue. So that's 9 minutes and about a minute for the telescope to move across the sky to the new object. So I'm trying to keep the telescope working. I'm not paying for the telescope time, but I'm conscious that if I only take one image in half an hour, that's a little bit of a waste of time. So I do want to sort of keep the telescope busy and then talk to you in the dark points. There are 3 images there. We can actually see the images are starting to drop into my account, if you like, at the bottom of the object, bottom of the screen as well. I'm not going to click on any of this yet because I have a feeling it might just disrupt what I'm doing here. So
Fraser, can I
yes,
raise a
please
question?
do. Please.
Actually, there is a question and a comment of mine. I think it's important also to mention that you probably are being careful not to slew the telescope to one side and then to another side. You make a sequence that makes sense so that the telescope moves, you don't waste your precious time in telescope moving here and there and there. It's just a sequence that makes sense.
Absolutely, yes. And that's sort of done, some of that's done with 16 years of experience. and just sort of knowing. Some of it's done by looking at the numbers, and for teachers especially, it can be done very well. There's a program called Stellarium. Again, you may want to put this in the chat somewhere, Rose. I'm sure you might mention it next week as well. Stellarium is kind of free planetarium software. It shows how the night sky will look tonight or next Tuesday or in August from any point on the Earth. You can go back to the day you were born, or you can go back to Christmas Day on the year 0, and you can see how the night sky was. That then allows you to kind of map out, and you're absolutely right. If you, how would we put an example? A really good example, I suppose, would be if you went shopping and you went to the vegetable aisle and you picked up a pepper, and then you went over to the other side of the shop and you picked up a bottle of milk, and then you went back to the vegetable aisle and picked up some mushrooms, and it would be crazy, right? You would just be spending all your time moving back from one place to the other. And incidentally, if you do have any vegetables, please send them to Britain because we've run out. But yeah, the idea here is that we're being a little bit clever. We're picking up all the objects that are relatively close to each other so that we're not driving the telescope too hard. We're not spending all our time just moving the telescope from one object to another. Just looking at the time. So it's 11 seconds on this object. And then I will try and
Can I shoot another question, or we wait for the next?
Let's see what this image looks like. We'll see if we can talk about that. And then I was going to come back to one other tiny point on that, and then we'll try the other question after that. So this image should change in a sec as the camera finishes exposing it, then sends that image. And again, remember, this image is coming from Australia. There you go. That's not too bad.
Wow, that's beautiful.
You like that one? That's quite nice.
No.
This is an object called 30 Doradus. Doradus being the constellation. Dorada it's a fish, right?
Yes.
Yeah. So 30.
Dorados is also gold.
Goat.
Gold, the metal.
Oh, gold. Okay. Yeah. Okay. Yeah. This is a star-forming region. This is an area in one of the Magellanic Clouds in the southern hemisphere. We cannot image this object from the northern hemisphere unless we have a robotic telescope, of course. It's a really, really bright white blob, and the reason for that is there are so many stars in there. But you can start to see some of the pattern. This is an area of gas and dust that is still forming stars. What we could do, I might not do it today because we might not have time, but thinking about it, because that central area is it's a bit of a mess, it's a bit too bright, we could go back and instead of doing 180-second exposure, we could do this again and try, let's say 30 seconds. I wouldn't go to 179, I would go from 180 maybe down to 30. This is where your hypothesis generator in the teacher's head comes in. Your hypothesis is, well, 180 is too long an exposure, let's try 30. Okay, if 30 is rubbish, let's maybe try 90, and so on. So you can kind of play around and just observe in that way. So this is the first image of this object. I was going to come back to one point that we mentioned before, driving the telescope. I was lucky enough a few years ago to go to the Very Large Telescope in Chile. And at the end of each night, they have a printout, and this piece of paper comes via email to you. Piece of paper comes via email. That's a ridiculous thing to say. You know what I mean? A PDF turns up, and it says you had the telescope for 11 hours last night. You drove it for 27 minutes. You exposed for 6 hours and 45. The time that was idle, the time that you were not doing anything was, let's say 5 minutes, 7 minutes. If that time that was idle was, I forget the percentage, let's say 1% or 2% of the total night, you get another email that says, please do not do this. This telescope costs $50,000 per night or whatever the value is. Please ensure that you have your act together and you keep this telescope going. We don't do that with this. We don't send you messages like that, but it is sort of in your head somewhere of the more that I talk to Rosa, Gustavo now, the more that I answer questions, the less I'm concentrating on actually driving the telescope to the next object. And there's a balance to be had there, of course. I think a second image came through because that one looks a little bit different, right? That one looks a little bit nicer. 11 seconds. Maybe this is the third image coming through. I am then going to drive somewhere else. So again, we finished exposing, the camera has exposed It's an electronic camera, and it will now send that data. So it drops the data from the camera into a readable form, which is called a FITS file, F-I-T-S file. That file then, I don't know, it ends up in the cloud somewhere. I suspect it goes from Australia to Santa Barbara to California, where LCO are based, and then from there on to me in South Wales, and from there on via Zoom to you all where you are. So this image has done quite a bit of traveling, not least because, of course, the light has come from a reasonable distance away in the first place. That's the third image. Rosa, we maybe can play around with those next week because they're quite nice images.
Certainly, certainly.
And again, if you look on Wikipedia or Google image that object, which is called 30 Doradus or NGC 2070, you will find images that look a little bit like the one we had there. I'm going to try one more object. It's always a bit of a gamble as to how many of these you can do in 30 minutes. 535.17 minus 523.24. And we'll do 120 seconds, so a slightly shorter exposure. And oh, I'm sorry. Okay, that's my mistake. I jumped the gun a little bit there. It's only taken 2 of the 3 images that I had, so it's still doing the third image of the Tarantula Nebula. It actually doesn't matter that I've put these numbers in. I'm almost looks like I'm pre-prepared and being professional again, but I've actually put these numbers in ready. At the moment, in theory, I could send the telescope to this third object, but it would mean that I would miss out on the image that I'm currently taking. The telescope would stop and go off to do the third thing I've asked it to do. So I'm going to sit tight. We'll let this one run another 70 seconds. Rosie, you had another question, I think you mentioned.
Yeah, there's another question from the audience. Wilson Canelo is asking about images. Is AI used for analysis?
In AI in education, no. In science, absolutely, yes. Yes, they are. Let's think about the numbers here. There are about 30 telescopes in the LCO network. Each one of them operates for, let's say, I can't do the maths here, but let's say 10 hours a day. So that's 30 times 10. That's 300 hours of data per day. Each image might be 5 minutes long, however many that makes that number, multiplied by 250 days of the year that the telescope works because of weather. That is, we're no longer in gigabytes. We're probably in terabytes, if not petabytes of data there. So yes, scientists generally have things like AI, things like a lot of coding is done in Python that processes images automatically. It does all the background processing. There might be a particular object in an image that you're interested in, which means that you don't actually care about the beauty of the image. You just want to know, has that little dot changed in brightness since 3 days ago, since a week ago, since 2 weeks ago? And yes, the more AI, the more automated you can make that process, the more that astronomers can go off and do other things in their lives. And that's certainly something some of the groups I've worked with have been able to do, is to write code, to write pieces of software that analyzes the data in real time. That's the third image. So that's that one done. Now I've got to go. I've got a green for go. So I'm going to go off to my third object. I've got about 10 minutes left. It says it's going to take 419 seconds, which is 7 minutes. So this is going to kind of work out quite well. If we scroll back up to the top, everything is green and yellow. The telescope is moving to the object. So again, as Rosa mentioned, the telescope is just doing a quick little jump across to the next object. It's found the object. It doesn't know. The telescope, as clever as it is, it doesn't know what the object is. It doesn't know whether it's pointing at a particular object. It doesn't know that I've put the coordinates in correctly. It doesn't know that that's a suitable exposure time. It's just doing, in a sense, what it's being told to do. So there's an element here of me making sure that I know what I'm doing. And that's something, again, we may have time to discuss afterwards, is how do you look at other people's images and what you do with that information that can allow you to choose your own images. We never want, and Rosa, and she has some very good teachers that have worked on these projects for a long time anyway, but we never want you to be sitting there thinking, I don't know what to observe, I don't know what numbers to type in, I don't know what exposures to type in. If you email and you say to myself or to Rosa, I have a session booked for next Thursday, what should I image? We can probably come back and give you some information or point you in the direction of finding that information for yourself, which is of course far better. You also, most of you have 20 resources, 30 resources in your classroom, which are your students. And each one of those can be set a little task to go off and do some of this work for you. So again, it kind of comes with experience, but there is lots of information out there that you can use to pull that information, or lots of places out there to pull that information together from. Our third object, we are 13 seconds away from getting the first image. So that's that's the third of the images of NGC 2070 on the screen there. And that should change in a second to another object. Just waiting to see, just sending the. There you go. Okay, that's okay. I know what this object is, and I know that that's not an awful image of it. Rosa, do you recognize this object at all? You might have maybe saw the numbers I typed in, right?
No, I didn't, and I don't recognize it. Isn't it overexposed?
It's a little bit overexposed, yeah.
I haven't paid attention.
Okay, if you turned it upside down, that would help.
Is it M16?
No.
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 I don't know.
Orion Nebula, right?
It's what? The
Orion.
Yeah,
Orion Nebula.
it's M42. There's a very nearby object called the Orion Nebula. It is just about visible to the naked eye, some parts of it in the center of the constellation of Orion, the Hunter. And there's an area in there, which is a black area that's known as the Horsehead Nebula. And I think it's that area which is actually at the top of the image. If you were to invert this image, if you were to spin this image by 180 degrees, you will see the Horsehead just sitting there. I tend to agree with you that 120 seconds is maybe too long an exposure for it. I have two options here. One is to let the telescope keep running, or the other is to change. You know what I'm going to do? I'm going to change this. Let's do this on the fly and see what happens. I wonder if maybe 20 seconds is a smarter exposure time than 120. Maybe I was a little bit more carried away. I'm going to click cancel. And what I hope will happen, I don't know if this is going to happen. Yeah. Okay. What I hope that's happened with cancel is it stopped doing what I was asking it to do. Well, that's okay, because we thought those images were going to be a bit rubbish anyway, but it should now take another command. And that command is basically stay on the same object. It's the right object. You're in the right place in the sky, but do the camera again, but just for 20 seconds. And I wonder if, as Rosa mentioned, it's a little bit overexposed. And I wonder if maybe this will work. And again, we can't do it in real time, but maybe between now and next week or during next week's session, we can spin that image. We can turn that image around by 180 degrees, and it will maybe just trigger something. You think, okay, yeah, I do recognize that. That is the Horsehead Nebula. But again, I've just found 3 objects today that I thought would work. I don't use this particular mode. I don't do a lot of observing in this way. So I'm sort of always trying to guess it. What was I going to say? There was something I was going to say then that I thought was really important, and I completely forgot it. Yes, there is a page on our website, and again, we'll provide you with the links hopefully at some point, that is called something like monthly targets. And in there, for every month of the year, we put 3 or 4 objects that are visible. So we do try and give you a little bit of background information, a little bit of a steer to some objects that would maybe work. And the other aspect of that, that's a little bit better. You've got to use your imagination a little bit, but if you can spin that through 180 degrees, I'm pretty sure that's the Horsehead Nebula. And we can play around with the color. The other thing you can do, it doesn't always work perfectly, but you can always try it. I'm in what's called manual mode. I'm typing in the names and numbers of objects that I've already done my homework on. If I tick this box here that says list, there is a drop-down menu. And this drop-down menu lists, what's that, about 50 or 60 objects. Now, I cannot guarantee that every single one of these will be perfect, but this list should be a list of objects that are currently visible, currently available, with an idea of exposure time. That can help. That can be quite useful. If you come to this session very short notice, or you haven't had a chance to do the preparation, just grabbing hold of this list and just clicking on these at random, or maybe having a student working with you who's looking through the Wikipedia images of these objects, or the fact that it does say it's a supernova, it's a cluster, they may be objects that are of particular interest to you. We have 2 minutes left, so we're going to run out of time, but I think these are the 3 images. So I think we're pretty much done on what we can show you today. If I scroll down here, this says session images. These are my images that I can download. There is a slider here, and you can see that there are images of the objects that we imaged: NGC 2070, NGC 1385, M42. Each one of those I can click on and download as a FITS file, or I can preview the image. Maybe I'll try previewing the image of one of these just to see what it shows me. Do you know what? Straight away, that preview image is probably 10 times nicer than the image I took, than the thumbnail. So these images that I'm sort of grabbing now, we haven't done any processing. What Rosa and I will talk about next week is much more about how you clean these images up, if you like. But that's not bad at all. I'm pretty impressed by that.
Really very nice, Fraser.
Yeah, and you know, I'm what I mean by impressed is I'm impressed with the way the telescope is done. I'm not impressed with what I've done. I'm impressed with what's happened there. I can try that with the M42 one and see what that brings out. Yeah, I mean, again, it's sort of processing this image. There's a little bit, I suppose, of AI going on here. The telescope software doesn't really know what I want to do with this image, so it's producing its best guess, if you like, of what it thinks I want to see. Yeah, they're quite nice. And then we can scroll up. We can have a look at the first object, which was the galaxy, and we'll have a look at one of the preview images again. Yeah, I mean, okay, that's okay. If we scroll in, yeah, I mean, so I can zoom in and out on the central part of the galaxy, on the central part of the image. That's the galaxy. It's not as spectacular as maybe you might have expected, but this is a very faint object. Like I say, 68 million light years away. So this is a galaxy that's quite a decent amount of distance away across the universe. I'm kind of happy to stop sharing at that point, Rose. I think we're done on telescopy stuff. So I don't know what you want to do to carry on now in terms of questions or anything that I haven't mentioned, or anything you want to mention ahead of doing this again next week.
Yeah, thank you very much, Fraser. That was super exciting. The first time I had an interaction with a robotic telescope, my first experience was with the Pillars of Creation, the M16, and it was a blast. And I immediately realized that that's the way that we should be educating the students, to help them become fascinated by the universe by taking their own images. There is a sense of, okay, that was mine. Maybe these images that you just took, maybe we were the only humans at this moment in time taking a picture of that object. And maybe in that region, there is some astronomical event happening that we didn't notice. And when we analyze the images, we might discover a supernova, or maybe an asteroid that passed by through the images, or although we won't be able to analyze that specifically, but there are so many different things that are going on in the universe, and we can bring this magical sense of, I am actually observing the universe. I'm doing what scientists are doing, that I think should be brought to the classroom. Of course, we realize that if a teacher, an educator never saw this procedure before, it might seem really frightening to do that, but it is not difficult. It's just a matter of understanding the concept and understanding how easy it is for you to do it yourself with your students. So that's our ambition this week and next week. So today we just showed you how we do it, how we observe with this robotic telescope. And next week we will show you, okay, now we have the images, what to do with them. And also because there are zillions of images available on the internet that you can actually explore with your students, and you might actually end up doing some new discoveries with your students. And this is what we would like to engage teachers in doing. So next week will be the continuation of this webinar, and the follow-up of that one will be maybe an online visit to your classroom where we can make the same procedure with your students. So I think this is a very good way to have telescopes invading classrooms in the planet. So Fraser and I are going to put our Space Invaders suit and make sure that we can infect you with this idea and that you will join us for that. I will put here on the chat a link to a form where you can manifest your interest to participate in future webinars. They're going to take place in the Learning from the Extremes YouTube channel, not in this one where you are now. From next week on, it will be another YouTube channel. And please disseminate this, tell friends that this is taking place, and come back for more. And I don't know if you have any comments or questions that you would like to put to Fraser. You can please write them on the chat. I just have thanks a lot, quite interesting presentation. Thank you very much for the tour de force. So people are saying that they enjoyed the presentation. And while we have a few more minutes, Fraser, I would like to ask you something. I know you've been an astronomer that actually traveled to the telescope, to the observatory site to take the images. And now we are faced with this situation where now we can take it sitting in our houses, watching our favorite series and, collecting images collecting images from robotic telescopes. Do you miss the trips to the mountains, to the very inhospitable places where we have these telescopes?
I guess I probably do, but I didn't do lots of them. I think there were people who, I remember talking to people who went to observatories in Chile, which to me sounds really exotic and crazy place to get to and to go and visit. But he spoke about going to Chile like you would speak about having to go to the supermarket or to the doctor. I'm going to Chile. And so sometimes I think there is a point beyond which, if you don't enjoy the travel, if you don't enjoy dropping into the culture and doing things, that sort of staying at home. I mean, it's better for the planet, right? I mean, the carbon footprint of astronomy, maybe it's not that huge, but to move the data around the world seems more sensible than moving the students and the teachers around the world. If today's session didn't happen because there was bad weather in Australia or somebody kicked a cable, or, imagine if we'd gone to, so Rosa and I do events like we go to the Canary Islands in the summer and we take the students and teachers up to, or the teachers are the students, we take them up to Teide. If it's a cloudy night, they get to see some stuff, they get to see some cool buildings, but they don't get to see the night sky. This is the key with this, I think, is you do it from your classroom. You don't have to, you have to do a bit of preparation, but if it doesn't happen, it doesn't happen. One thing, you sort of reminded me of something as well there, Rosa. I've really only been talking about what's called real-time mode. So the real-time mode of the telescopes is what I showed you, these 30-minute blocks. It's your telescope or my telescope for 30 minutes, and you can press as many buttons as you like. You can go to as many different objects as you choose. And at the end of that 30 minutes, the telescope goes to the next person or the next group. For some teachers, and for most astronomers and scientists, that's not a very efficient way of working, because it forces you to particular times and there's particular parts of the night sky you can't access. So most of our observations are done in what's called a queue mode or queue schedule mode. I haven't shown you any of that today at all. It would take another 20 minutes to go through it. But the idea is you're kind of putting the same information in, but you're not saying, I want, I have the telescope now. You're saying, you know what, I'd like an image of M42 and I'd like it in the next week. It doesn't have to be today. It doesn't have to be tomorrow. But by, let's say, Saturday or Sunday, I would like that image back. With the question about AI, that's a really smart way of the telescope knowing, okay, I have 5 requests from this guy in California. I have 3 requests from this guy in Cardiff. I have 5 requests from this lady in Portugal. And it works out the smartest way of doing them, maybe by priority, maybe by how important they are, if you like, but also by which are the longest observations, which fit the observations, which drives the telescope the shortest amount of distance from one object to the next. So that queue scheduled mode is very, very useful. And it sort of helps answer your question, I think, Rosa, that the queue scheduled mode means I don't have to only image objects that are visible at 9:30 from Australia. I can image an object that is visible only from the Texan telescope, or the one that's in Tenerife, or the one that's in South Africa. And again, that makes the network very, very effective. Hopefully that answers some of your question, at least.
Well, there's also this sense that, the universe is so big, and actually sitting from our houses, we see the stars, but we don't actually understand what they are and what's going on. And actually, in the last few nights, we have this beautiful show of the moon and Jupiter and Venus, dancing around each other, and people don't really understand how powerful it is, the possibility to go more deep into the universe and actually understanding our origins. And as much as it might seem not important to us, it's why we know everything we know, and we know how important it is to preserve what we have here on Earth. So yeah, Fraser, there is another comment actually too. Thank you, very cool, very motivating. Thanks, Rosa and Fraser. Well, we thank you for spending your time here with us. And we would like to just mention again that these webinars are going to be bi-weekly. They're going to take place every 15 days on Wednesdays, 4 p.m. CET. Today was an exception, and next week is another exception, because we are going to analyze the images that we have taken today and also introduce you to a very nice software to analyze those images. And so please keep tuned to our social media channels, where we are announcing these events. I can give you also the link to the website of the project. Let me just copy it here and give you where you also will find information about this. And these webinars that are going to take place, we have virtual visits, we have machine learning, artificial intelligence, we have understanding better learning from the extremes. We have a big list of interesting topics and interesting people to bring to you. So I would like to thank you very much for participating. I would like to thank Fraser a lot for making magic happen today. And I hope to see you all soon.
Yeah, thanks for me, and thanks, Rosa, for looking after me as well.
So see you next week.